Okay. So, we know what we have to do today. Okay. So, as we discussed last night, we will be talking about so we will be talking about the following problem, which is called above guarantee vertex cover, like, and you can define what guarantee is. So we have our guarantee will be linear programming relaxation. Okay. So now generally people write linear programming for vertex cover and G because it is very clear to us that what we are going to talk about, we will omit that and we will just stick to linear programming. Okay. So input is graph G, an integer k, and the question is, same, the G has a vertex cover of size at most k, okay, and the parameter is so in essence we need to design an algorithm with running time. Okay. So that's our goal of the day. Okay. So should we start with just an algorithm? What do you think? The algorithm could be very complicated, should be very complicated. Now, by now you know several algorithms for vertex cover, right? So there were very complicated algorithms for long time. But actually, so here's an algorithm. You have seen this algorithm several times. UV, right? Either U belongs to a solution or V belongs to a solution, right? And that was 2 to the power k vertex cover algorithm. So algorithm is this. That's it. So really algorithm is just this much, but of course we need to add how pre-processing steps interfere with some of these things, and that allows us that this simple branching algorithm to have running time of this nature. But as an algorithm, this is all that it is. Okay, is that fine? Okay. So now, I mean, I didn't get your question. Yeah, but that is exactly what we have to figure it out, right? Why this simple algorithm can also be this is all I tell you, that it's not that we are going to design some very complicated algorithm. All we are going to understand and analyze that why this simple algorithm can also be interpreted as this, because there are a lot more things can happen, or lot more things happens if we try to understand the effect of those reduction rules that happens. Okay, but as an algorithm, this is it. Okay, so that's all that I'm saying. Okay. Okay, so now we will go back and forget this algorithm and try to build some properties of how vertex cover LP looks like, and then come back and utilize those properties to design such an algorithm. Okay. So remember, I proved the following thing, that so suppose Y is solution to linear programming of G. What I mean by solution to Y? So think of this Y as a vector, which is like y1, yn, where you have v1 to vn vertices, and the values assigned by Y is like y1, y2, y3, yn to the corresponding, right? So what we showed to you that, look at the set V, which is equal to 1. So what was this? Okay, so those vertices such that those Vi such that yi equal to 1, right? And then we said there exists an optimal solution such that, okay, no, my bad, it was this, right? And what was V equal to half, if you recall correctly, Vi Yi equal to half, and let's call it V0. And today I will make it clear why are we calling the way they are, okay? Why I'm calling it 1 half and this. I have used it before, and so what was this? This is all Vi Yi less than half, okay? And what we showed, there exists an optimal solution, or there exists an optimal solution means optimal vertex cover S such that there exists an optimal vertex cover S such that S contains V1 and this is contained inside V1 union V half. Yeah. Okay. So this is what we proved. This is what we proved, that there exists an optimal solution which contains every vertex which has been assigned in V1 and it does not contain any vertex that has been assigned in the set V0. Okay? And we proved this lemma, and this is how we got, if you recall, 2k vertex kernel for vertex cover. Okay? Okay. Now I will tell you why equal to 1, equal to 0, equal to half, because we will show now that there exists an optimal LP solution. Okay? So it's a lemma. There exists an optimal LP solution, y1 to yn of LP of G such that yi belongs to the set 0, half and 1, right? So if I look at a polytope of a linear programming, or there exists an optimal LP solution where each yi takes value either 0, half or 1. Okay? So this is why people write like this. Okay? So we'll prove this because we will need this to analyze this particular algorithm. Okay? But this is just a combinatorial fact which is, okay, it has nothing to do with algorithm. This people have known from 70s itself. Okay? When people were studying vertex cover polytope, maximum matching polytope. So people already had observed some of these things long back. No. Of course, it is completely dependent on the vertex cover. It is like optimal LP solution, like I should say, there exists an optimal LP solution. Okay, there exists an optimal solution to LP of vertex cover. Okay, this. So I told you I'm only talking about a fixed LP of vertex cover, right? And I'm saying that there exists an optimal solution to the linear programming relaxation of vertex cover LP, where each values either is 0, half or 1. Okay, there are very few things for which this nice property holds. Okay, there are like the generalization of vertex cover where you can show that there exists an optimal. Look, think about it, right? In integer linear programming, I want values to take either 0 or 1, or maybe some integer. But if I'm talking about 0, 1 integer programming, then either 0 or 1. When I allow LP relaxation, means I allow these variables to take values which are rational. So I allow it unbound. Now, still, I'm telling you that look, it's like, but can you come up with an LP solution, linear programming solution, where you are not using the whole of Q, but you are only taking these three values, 0, half or 1, right? So this is very, let's say this is a very, like even for, this is a very special property of vertex cover LP. Okay, so most for most problems you can't come up with such discrete sets where if you look at the optimum value over those discrete sets and you look at the optimum value of LP over Q is same, right? So what does this tells us? That look at vertex cover LP. So what is, right? Okay, and such that what is the constraint for all UV in E of G 1 and for all V in Vg is greater than or equal to 0, right? This is the constraint, right? Now what are we looking for? Now actually we are looking for a solution here. Say we are looking for a solution Y which is basically I'm allowing it to take values in Q power n, rational. And here what I'm saying, look at this values here. What are we saying? This lemma is telling us that if you do optimization over these values and you do optimization over Q power n, it just happens that for this minimization you can, like, the minimization over this is equal to minimization over this number. So this is very, very powerful, right? Because here what are you saying? Look, I gave you so much power of every coordinate can take rationals, and I say minimize it, and the value what you are able to achieve for this problem is same as if I would have asked you that try to minimize your LP value, the optimization function over the coordinates where you are allowed to only take 0, half or 1, right? So I could have why 0, half and 1. People could also take any discrete set and try to optimize. But in general, optimization over Q and optimization over discrete sets may not lead to the same set of solution. Okay, so this is a very special property about this vertex cover LP, that optimization over Q and optimization over discrete set 0, half and 1 are same. Okay, so at least you understand its proof is very simple, but the fact is very nice. Okay, so let's try to prove this. I'm not going to assume it, we're going to prove it. Okay. Okay, so what I say is, like, let me, for a contradiction, so this is by contradiction, choose Y in Q power n. So among all the LP opt solution, choose which maximizes its coordinates in so there could be many LP solution which minimizes my LP like this optimization. Among those, I said take the one which has maximum number of coordinates from either 0, half or 1. It's possible that you have none, then it's 0, right? So I have chosen the one which is this. Like, you will see that this is what we are going to do, actually is going to provide an algorithm to us. You start with any LP and you can do some changes and you can keep doing it. Okay, so what will we do? So basically we will take this LP and do some fudging around this LP and do something. Okay, but since we are trying to, so if I want to show that Y exists where each coordinate is 0, half and 1 is just if I can come up with another Y prime which contains more number of coordinates in 0, half and 1, then I'm done, because that contradicts the fact that Y was the one which had maximum number of coordinates from 0, half or 1. Okay, so now we will do some tinkering with Y and try to get this. So what I'm going to do tinkering is that, look at, I have value y1, y2, yn. So first of all, I do not want to touch anything which already is 0, half or 1. Okay, I do not want to touch those because those are good for me. So like I want to have a optimum solution to this, which has more numbers of 0, half, and 1, then let's not touch these things. Okay. So now half, 0, this is 1. Okay. Now what I'm going to do, pick up any value. Suppose some value is here. Okay. For some I, yi is here. Okay. So I ask myself, what is the distance to 0? This is one thing I would be interested in. What is his distance to half? And what is his distance to 1? Okay. So I said, look, I would say that this vertex would prefer to go closest, right? So among all these three values, I would say, okay, if at all I would like this value to move to 0, half, and 1, I will like it to move it to the one which is closest to him. Okay. Okay. So for every I, so what is it? And what we know that yi is not element of 0, half, and 1. Okay. Otherwise, let's not touch it. Okay. So if what is this value is? What is its closeness to 0 will be? What is that number?
Some value less than half.
No. But for this particular guy, how much does he needs to go so that it becomes 0? Its value itself, right? So it is minimum of yi, the value, or what is its distance to half? And distance to here. Okay, fine. Okay. You say that, okay, for these guys, why will you care about this anyway? So I just want to, okay. But now imagine my value would have been here. It could be that this, if you, right? It could be somewhere here. So what is its possibility to go to this? Then it is going to be still yi, but now what? Now it is yi minus half, right? And what is this? Okay. So if I have to combine these things, I can just put a mod, right? So basically what happens, for every variable, irrespective of where you, if you are not equal to 0, half, and 1, the distance that you could travel is minimum of these things. Now what I'm going to take is minimum of all these guys, right? So my epsilon is going to be minimum over, okay, yi minus half, or let's call it half minus yi, 1 minus yi, okay. And what is the property of this? Yi does not belong to 0, half, and 1. So this is minimum of some bunch of numbers. So the way I have taken yi, I know that epsilon is greater than 0, right? Because I have not picked up those values. For every yi, all the three coordinates are non-negative. Notice here, right? So if you are taking a max over some bunch of non-negative numbers or non-zero positive numbers, then you are going to get the same thing. Okay. So epsilon makes sense. Now the help of this epsilon, we are going to get a couple of solutions from here, okay, and then we are going to argue something nice. Okay. Okay. So first I'm going to make a solution called y prime. So what is a y prime? Okay, and I will also make another solution called y double prime. So what is y prime? I say, okay, fine. Okay, so y prime of some vertex I, okay, some vertex I is yi prime. I check if yi belongs to 0, half, or 1, then this is yi itself. Look, I am not going to make you change. Okay. Now, so it is not among these. If yi is less than half, okay, if it is less than half, I am going to decide to do yi plus epsilon. Okay, and if yi is more than half, minus epsilon. Is that fine? That's my solution. Like, that's a potential solution. What happens, what doesn't happen, we'll worry about it later. I just want to claim to you that y prime is a feasible LP solution. Claim. Y prime is a feasible LP solution. Forget about like, I'm not care about what we did. All I'm trying to tell you that it's a feasible LP solution. Okay. Now let's look at why. First of all, notice no vertex which was greater than half crossed this. Like, no vertex can cross this, because if you are here, I mean, you have closure is half, right? So either you can go to half or you can go to 1, but you will never go to 0. And if you are here, you will never cross this side. You will only go up to half, right? Or 0. So this is a property is that whatever yi you took here, in yi prime, the corresponding guys either stays put, or if you are strictly less than half, it can go between 0 and half. If you are strictly greater than half, then you are between half and 1. That property holds. Okay. So why am I saying this? Is that look at all those. This is like with respect to y, all those variables which get strictly less than half, all those guys who get strictly greater than half, and all those guys who gets equal to half. Right? Now look at any edge. There was no edges here anyway before, because right now look at any edge here. You, for this vertex you decreased, you increase epsilon, and for this guy you decrease by epsilon. So this value, it was greater than 1 before, it still remains 1. Right? Here you might have decreased, but you are still, every value here is greater than half. Nothing would happen. So look at any edge here. Right? The values of these guys has decreased by how much? By epsilon. But still all these guys are greater or equal to half, so nothing happens to the edges here. And edges here, you decrease 1 by epsilon, increase 1 by epsilon, you decrease 1 by epsilon. So okay, so that's one solution. Okay. Okay. Now let's create another solution. So what is another solution? Is I'm going to make y double prime. What is y double prime? It's basically ulta of it, opposite of it. So it is still yi if yi is element of 0, half, 1. Okay. But now I'm going to do yi minus epsilon if yi is less than half, and I'm going to do yi plus epsilon if yi is more than half. I claim this is also a feasible solution. Okay. Claim y double prime is a feasible LP solution. Okay. Okay. Why? Because same argument, nothing would happen, right? Because what happened? This is, let's look at v greater than half, v less than half, v equal to half, right? So what we did, right? So the people look at this edges here, right? Now what happened for the edges here? You decreased here, you increased here, right? But nobody, again, nobody, and this side, do I care anymore? I mean, these guys' values can only have, you have only increased by epsilon. So if some edge was satisfying 1 with those values, by increasing something more, you can satisfy even more. So I don't care about edges here anyway, and there are no edges here anyway. So this indeed is a feasible solution. But what can we say about? Okay, so these are both are feasible solution. Okay, and what is the property of both feasible solution? Y prime has strictly more coordinates in 0, half, 1. Why? Look at the one for which this is epsilon is minimum, right? That guy will definitely go to either 0, half, or 1, right? Right? And that's it, right? So y double prime has strictly more coordinate in this. But we are not done. How do we know this value is equal to the value of y? All we said, y prime is a feasible solution. Y double prime is a feasible solution, has more coordinates in 0, half, and 1 than y. But we are not interested in any feasible solution, right? We are interested in a feasible solution whose value is equal to the value of LP. Otherwise, we could have just taken all 1, no? That's a feasible solution. Every coordinate is in 1, 0, half, and 1. Or why that? You take every value to be equal to half. That is also feasible solution, right? Okay. Okay. So, okay. So what happens now? How do I show that y prime is equal to, value of y prime is equal to y, value of y double prime is equal to y? You get my point? Isn't this what it is, right? Because look at a particular guy, right? In one you have added by plus epsilon, in the other you have decreased by minus epsilon. So those guys will cancel, 2 times this divided by 2. So y is basically this. Agreed? And the value which you never changed, you never changed. It's like it's only going to get double, so if you divide by that, you're going to get that, right? So the values which you changed, look at some value. In one, you are minus epsilon with whatever value. In other side, you are going to be plus epsilon, right? Look at this, right? So if you sum those coordinates, what are you going to get? Yi minus epsilon, yi plus epsilon, which is 2 times yi divided by 2 is yi. Agreed? Okay, excellent. So now what can you say? But y prime is a feasible solution, right? So value of y prime is only going to be equal to value of y plus something. Then value of y double prime is value of y plus something. Okay, but then if suppose y prime is y plus x, not say alpha, when y double prime is y plus beta. When I say just sum the values, right? We know that this happens where alpha is greater than or equal to 0, beta is greater than or equal to 0, because y prime and y double prime are feasible solution, and hence its value can only be more than my LP value. Okay, if this. So y is basically y plus alpha plus beta by 2. How can y be equal to alpha plus beta by 2, and when can this happen? When both alpha is equal to 0 and beta is equal to 0, which implies that y prime is equal to y, y double prime is equal to. So what happened? We just wrote y as a linear combination of y prime and y double prime. That's it. There's nothing more fancy happening. Okay. So what you have shown that y prime is a linear combination of, and whenever you can write linear combination, so I could have written linear combination of 1, 2, 3 things also, then it would have happened. Okay, which implies y is equal to y prime, y. When I say equal as a value, I'm not talking about equal as a coordinate wise. Okay, so you have to be a bit more careful with what maths I'm doing here. Okay, but what does this shows? But does this gives us an algorithm? So what we have shown that we can actually, so for the proof it's okay, it's a contradiction because I have been able to produce either y or y double prime which has more coordinates in 0, half and 1, right? So that's, is it true that y double prime has strictly, one of them has, I don't think both has. I think both does not have, only one of them will have, notice, because look at the minimum guy. So either, so it is minimum, suppose you are here. So your minimum is either this side or this side. It can't be both, right? So for that variable, in one of them you go to the right side, then you become 0, or you go to the right side in the other. So this only one of y prime and y double prime has strictly more, not both.
Why not both? Because we are subtracting or adding.
Okay, suppose epsilon is a minimum. So suppose minimum is, suppose this is some guy y for which minimum is achieved. Minimum is minimum of 3 numbers. So either this is minimum or this is minimum or this is minimum. Suppose this is minimum. So when I do minus epsilon, I get 0.
Yes.
And in other what I do? Plus epsilon. Why will I go to half? Right? But I know it at least in either y double prime or y double prime, you are going to the place like, so for example, if for this guy minimum was this, right? So what happens when you are adding, in that side when you are adding plus epsilon, then you are going to the destination. So you will only go to the destination, right destination in one of these things. But that is good enough for us because what is the property of this? Both of them are feasible solution. Okay, both of them are feasible solution. Both of them has value equal to LP, and I know at least one of them has more coordinates in 0, half or 1. Right? Okay.
Why cannot both have more coordinates?
I cannot prove that.
Okay.
It could.
It could.
Yeah, maybe this is like, it is 1/4 here, this is 1/4 here, 1/4 here. Of course it can have. But I cannot guarantee. But in the worst case, this is what I can guarantee. Okay, fine. But so what is an algorithm to compute this? We actually described a polytime algorithm. You start with any LP, right? You start with any LP, right? You start with any LP. Can you compute this in polytime? I have given you this value. You can compute this in polytime, right? Look at that epsilon. Go to whichever is like, you know, both of them work, right? So now you make one of those guys to epsilon, you're done. So you have increased the coordinate by 1. Again, this is a feasible LP solution. The proof tells me I will again find another epsilon with respect to the new LP values. But how many times will I do this? At most n times, right? So at the end of this process, I would have found an LP values for every one of them, which is either 0 or half or 1. Okay, so this does provide an algorithm to compute a 0, half, 1 integral solution if you start with, initially if someone has given you an LP solution. Okay, okay. So we have shown this, and what we have shown further we can compute such a solution in polytime. We will see now. Imagine.
I have one question. So here we are saying there exists. That means not all optimal solutions are in this form.
No.
Oh, okay.
Not. Because I could start with initial LP, which may not be of this form. Okay, your question is very valid. Why do I care about this LP than the other LP? You are right. You will see its importance in designing our algorithm. Okay, so K minus LP is a quantity. This is a quantity, right? So if I'm doing my branching algorithm, what would I like it to happen? That I would like this quantity to change in both direction, right? Look, if I want, look, I'm just doing this branching algorithm, right? Pick an edge, branch. I need to control its depth, right? because I know breadth is anyway 2, so that's okay, but I need to control depth. What did I use last time to control the depth? I said, look, the solution that you are seeking at every branch is reducing by 1, so you cannot have too much of depth. Now I need to find some way that, some measure or some way that I want to say, look, actually now the quantity that needs to change is not k, it's k minus LP, because that is what is in your control. So if I can devise a branching algorithm where I can say, look, the depth of this tree is bounded by some function of k minus LP, I'm done. Right? Now, if I start with any arbitrary solution, the LP which I start with and the next stage, the change in LP that happened, it could be very close to each other as a function of n. Right? Then I can only say that depth is 2, like a function of n. But if it changes discretely, then I say, hey, you started with something, every step you are losing some good fraction. So then, as a just function of what you started with, you can go quickly. So that is why for this algorithm, this is nicer solution than I starting with any other LP solution. But now we need to implement this idea, okay? But for people in community, look, but as I told you, algorithmists did not discover this. It's a combinatorial optimization, people discovered it, right? And there they have a different objective. It's like how much, like how far it is from the, like it's like people like to optimize as much as possible, right? So if you're able to optimize over just small discrete space, it's much better, right? So then you start to have some combinatorial algorithms and this and that. Okay. And another reason was that if you write the vertex cover LP on bipartite graph, it's integral. Okay, so you can come up with 0, 1 optimal solution on bipartite graph, and that is basically what Hall's theorem is or Koenig's theorem is. This is precisely what it is. Okay, so LP provides an alternate way to all those graph theory lemmas that we have seen in everything, which even I could probably write the what I will try tree packing on this. I'm sure there will be a way to write LP and show some integral way of doing it. Okay, and that will show whatever it. So somehow all these things are combinatorially related. But I know that in general graph, vertex cover is NP hard. So now I ask myself that, okay, it is not integral, how far or how close to integral it can get. So I think that was their motivation to study these kind of things. Okay, and it just happens that people are able to use that. And also notice what is fun things. Okay, because of this you get immediately factor 2 approximation. Because of this lemma. Normal LP would not allow you to do so, because you can do immediately rounding. You round. Look at the values. Okay, what I do. So I will do every 0, keep it to 0, every half round it to 1. What's the value of this LP? You understand my point? No. I want to say that given this 0, half and 1, okay, why even combinatorial optimization people do it, let me explain to you in a minute. Okay, so now given this LP solution, I want to get an integral solution which value is as close to LP solution as possible. Okay, so in approximation algorithm, we first write LP, solve it, and then the second step is to round it to an integral solution and show that the integral rounding is not too far away from the LP rounding, and hence that too far away is your approximation factor. Okay. So now I solve my vertex cover LP and I got 0, half, 1, right? So what I do, so look at yi. If it is 0, keep it 0. If yi equal to 1, keep it 1. But if, yes? Someone is sleepy. Okay, and if y1 is half, you make it 1. So what is so summation of yi is your LP solution, okay? And suppose this is like yi prime, which is an integral solution, by the way. And now if you notice that this is also a feasible solution, because what you have done, you have only increased every value. So if those, but now it's an integral solution, right? Either 0 or 1. How far, so this is your LP solution. I ask yourself, what is the value of summation of yi prime in terms of summation yi? Look, even if this did not exist, if everybody was half, what you have done, for each of them you have made it twice. So summation y prime is twice summation yi. So what you have got? You have got an integral solution whose value is at most 2 times the LP solution. So what happens because of that? It's a factor 2 approximation. Now, this is why this is better solution than a normal LP solution, because now if you are closer to say 0, where should I round, right? Because now if I start rounding someone to 0, someone to 1, it is a bit more difficult, no? Because now what I have done a very trivial rounding. Anything which is non-zero, make it 1, right? This immediately allows feasibility. So this is where if you can show that these kind of things happen, so whatever is the minimum integer you will say, that will become your ratio and factor. So this is why these solutions are much more desirable compared to any LP solution, right? So generally what people do is that, yes?
Hello, sir.
Yes?
Sir, for vectors, we don't need this habitual solution. I mean, if the value is greater than equal to half, make them 1, and if 1, then 1, and less than half, then make it 0. Then
Just try to prove why it is, just try to prove then that it is a 2. I'm not saying that you can't prove, but it is not obvious, right? Then I have to show that the number of people I made it 0 and the number of people I made it more than half. Look at these quantities, somehow I have to relate it in a non-trivial way. I never said that you cannot do it in other way. There are 1,000 ways. All I'm saying that if you have such nice object, then rounding becomes very apparent, right? But of course you can do those, because this is what we have been doing even for the algorithm. But how let's say even for the kernel question, right? When I proved that, look, it lies between all all 1 is part of the solution. I had to show to you that the people who you could go in 0, I can move it to 1, and number of these objects are not less than. So I had to do some sort of gymnastic there. But for here, just round it, and then you are done. So I'm not saying that this is the only way. All I'm saying, if it is available to you, you can just blindly do it. Okay. Okay. So far so good. So this is like, at least you should feel convinced that this is important. This is interesting, right? And if this happens, we can do many things, okay? So if you look at any approximation algorithm book, they use this kind of thing to give you some first non-trivial approximation, okay? Okay, now what, okay, but we moved far too away, okay? So now I'm going to rub this and we're going back to the our algorithm, which we want to study. Okay, now for algorithmically, why it is interesting to us is that, look, now we realize that the solution lies between 0, half, and 1. But if my solution had some zeros, what is that it implies? I will also have some 1s, no? Like, you assume that you do not have isolated vertex, and some LP has 0, it means some people will also take 1. And if some people take 1, what happens then? We have reduction rule. Right? Remember, we said there exists an optimum solution containing all 1s. So if I can come up with a solution, so only time when I cannot make progress is when all half is the unique solution. Because, but there are 2 questions. How do I know that all half is the unique solution? That's one thing. Okay, and maybe I start with this algorithm or this routine and I get 0, half, 1, but all half. But maybe there is some other solution where you can do some gymnastic and make 0, 1, and half, because that will allow us to reduce something, right? So what I mean is the following. Okay, so this is what it is. So we all in FPT algorithm, we like this because it's like 0, half, 1, and I'm going to assume that if there is an isolated vertex, those are going to get 0. So that's anyway, if it is 0, you can just delete it and pick all its neighbors, right? But if there is no 1s, but there are only 0s, which means those are isolated vertex, right? So if this is V0, we have no delete and V1 include, right? So this we have a reduction rule for this. So it's a great, okay? So I am not able to apply any reduction rule. Why? Because what happens is that all yi is equal to half. So our solution is basically half to the power n, right? So the value of LP is how much? N over 2. If there are n vertex, what is the value of my LP? N by 2. Now I ask myself, is it really that I understand that the LP value is n by 2? Is it really that I can't do some of these things, or I can come up with other LP solution where LP solution whose value is n by 2 but do contain zeros and 1s. How do I check this? Or in other words, how do I know that all half is a unique solution? How? Okay, how do I know this? We'll come back to this for a minute. Okay, we'll come back to this. That suppose I knew how to prove this, that all half is a unique solution. What can I do then? Okay, what can I do then? Okay.
All vertices have half LP.
Then
There is a perfect match. For one vertex, there is another vertex. There is a match.
so you are saying this graph has perfect matching.
All half is
That this graph has perfect matching. I don't know. Maybe it's true, but like I don't know. Maybe it's true. How do you pair them? I don't understand. Like all half is always a solution, always a feasible solution. I'm not saying it is an optimal solution. Assign every vertex half. Look at every constraint is satisfied. So it is always true that LP solution is at most half the vertices for vertex cover. Okay, but there are something more. I want to go back. So what I said to you, that I am going to just do this algorithm UV, G minus U, K minus U, G minus V, K minus V. This is what I am going to do, algorithm wise. But if I want to, like if this is an algorithm, okay, branching factor is how much? 2. If we can bound the depth by function of K minus LP, then what will be if the depth can be bounded by this, then what is the running time of this algorithm? The running time of this algorithm is basically 2 to the power depth, right? 2 to the power depth, which is 2 to the power function of K minus LP, and then we are done, because it is some another function of LP. So if we can bound the depth by this, let's call it mu, just to look nice. Okay. So what is the meaning that this is bounded? It means I should be able to show I started with some K, some LP value. Next time K bent by K minus 1, LP value also bent by something, LP value also bent by something, and this change is small. Okay. So let's assign, let's call mu is k minus linear programming solution of G. So this is my measure. Okay, I want to see how this measure changes across different branches. Okay, okay. So now I'm going to call this graph G prime. Okay, so what is the mu of G is this. Mu of G prime is how much? It is k minus 1 minus LP of G prime. Is that okay? Okay. So what it change? Change is, what it change? Delta of change is mu of G minus mu of G prime. How much did the measure? Like in the beginning when I was k was solution size, my k minus 1. So change was 1. But now we have to be careful. So let's look at this. Now what is mu of G? Mu of G is k minus LP of G minus this minus this. So it is k minus 1 minus LP of G prime. So minus k minus minus plus 1 minus minus plus LP of G prime. Is that fine? Right? So k and k is going to get cancelled. Now what is this? Change is 1 minus LP of G minus LP of G prime. This is my change. Is that fine? This is my change. Now, if LP of G prime becomes too low, what happens to this change? If LP of G prime becomes much less compared to LP of G, right? Suppose this is 5 and this becomes 3, then what happens to this measure? It's negative. Nothing changed. You get my point? So if I want my measure to change nicely, it is in our, what is it called, benefit that LP of G prime is as close to LP of G as possible. If say both are equal, then how much do they change? By 1, right? So if you get my point, so if LP of G and LP of G prime are too far away from each other, then I can do some funky things. Okay. So now let's ask, if I had a graph where all half was the unique solution, suppose for now we have not reached there, but suppose all half was the unique solution, then what kind of dynamics we have on this kind of graph? Okay. Okay. So here is a G, and what I have done from here, I have deleted, this is G minus U, right? This is G minus. Imagine that the LP value of G minus U is strictly less than LP value of G, of course this is strictly less than, because, okay. So LP of G minus U minus 1 is this, or rather LP of G minus U is less than equal to, say, LP of G plus 1. It at least drops strictly less than 1. Like if you had 5, now it has become 3.9. What can you say then? In this case, I say this is impossible. Why? Because look at G minus U. Right? Look at this Y tilde, which is an LP value of this. Okay, let me get an LP value of G. What I'm going to do, LP value of G? What is this graph? It is U deleted everything else. Okay, I'm going to assign, okay, let's not call it, okay, something. Y of U, I'm going to assign 1. Is it a feasible LP now? Every edge here is taken care of them, and look at the edges here. It's taken care of this. So it's a feasible LP, but what is its value? Its value is LP of G minus U plus 1, right? So this is, which is less than equal to, have I written this correctly? Yeah. This is fine, no? So this is upper bounded by, and this is less than equal to LP of G. Is it true? If this is the case, then this is true, right? Or have done something wrong?
I think this is LP of G minus U. There's an LP of G minus 1.
No, this should be this,
Yeah.
right? So even like LP of G minus U has how much it dropped by. So basically, or it should be is this. LP of G minus U is even less than the LP value of G minus 1. Okay? So now what I stood, okay, I said if that is the case, then you start with LP of G minus U, you added Ui to 1. What is the value of this? This is strictly less than LP of G. Right? Is it possible? Look, forget about all half or this, that's not what I'm talking. But this cannot happen. So what is the meaning of this? So if you delete a vertex, the LP value has to be less than equal to this. This is fine. So it can only change by 1. Is that fine? So now let me tell you how much can they change. Okay. Okay. So now this tells us, suppose this is LP of G. I am asking you, what is an LP of G minus U could be? LP of G minus this is element of, either it can drop by 1 or it could be equal, no? Or it could drop by how much? Our all, look. So look, I know that the change between them is at most 1. But you said it has an integral solution, 0, half or 1. Right? So if all the solutions are 0, half and 1, so the change can be either 1 or 0 or half. Only 3 things possible, right? Anything below we know that it is not possible. So you have come down. You have come down. So look, if you sum these values, it's a multiple of half. Think of this way. What is the value of LP in any graph? It's a multiple of half. Because every value is 0, half or 1. Right? So think of this way. This is some alpha times half. What is this? This is beta times half. This is what it is. But they all are multiple of half. Right? So, okay. So what multiple of half you are changing? So, okay, fine. So alpha times some alpha times half, some beta times half. Beta into half. So, and I know the change is at most 1. So either you lose 1 or you lose half or you lose 0. That is fine. Is that okay? Right? Because it is just a multiple of half. So I know that it belongs to here, here, here. Okay. Okay. This is great for us. No change, it's great for us, right? If they, what is no change? Means this and this are equal. Our drops by 1. Okay, if the change is half, still it is okay. At least it changed by half. What is not okay? If LP of G minus LP of G minus 1 is 1. Right? But then what happened? Some magic happened then. But even if it is equal, change LP of G minus LP of G minus 1, it's a equal to 1. What happens then? Okay, take this guy, okay? This is LP of G minus U, and this guy I'm going to assign 1. What is its value equal to? Exactly equal to? If I do this, this is exactly equal to LP of G. But what we have been able to do then? What is wrong? We have been able to come up with an LP solution of G which is not half integral. But you said that only like there's a all half is a unique LP opt solution. But here you have been able to come up with an LP solution. If my LP of G minus U dropped by 1, then you can take that LP, assign this value to 1. That also provides me an algorithm in a minute. Think about it, okay? It will tell us how to check whether all half is a unique solution or not in a minute, okay? So what did it happen, okay? So what did I do? I said, okay, look, if the change of LP values of G minus U and G is exactly equal to then you take all these guys, whatever that G minus U LP assigns, and assign this U to 1. Now what happens? Drop is exactly equal to 1. I have assigned 1. It's still a feasible solution, but it's a feasible LP solution whose value is same as any LP solution, but it contains some non-zero, non-half entry. But you said to me that all half is a unique solution. So this cannot happen. So what is the only thing which is possible to happen? Zero or half. In which both case we are happy because drop changed by half. Okay, so both cases drop happens by half. So if that is what should be an expected running time of this algorithm? We have to prove lots of things, which I have still not gotten into, but we have to prove this. But like our algorithm is more or less done. Okay, so why all half is a unique solution? We have to verify, and there are many more things that we need to verify, which we will come in a minute. Okay. Okay, but so what is the running time of this algorithm? So what's the running time of the algorithm? If you look at the measure, what is this? T of mu change, T of mu minus, how much did it change in the next? By half, right? Because this, like in the worst case, it can only, at least it is definitely half. And two such problem. So what does the running time is? It is 4 to the power mu, which is 4 to the power k minus LP of G. Okay, so it's not very inefficient algorithm. It's quite efficient algorithm. We'll make even more efficient algorithm for this, but that requires different set of ideas. But let's first complete this algorithm. This algorithm is completely incomplete. Why it is incomplete? Even if I give you this fact, I tell you this algorithm is completely incomplete. There's something wrong. There's something. No, this is correct analysis, but there's something not right about this algorithm. What is not right about this? When did our previous algorithm, it's a recursive algorithm, no? So what recursive algorithm should have? What should have? Base case. What is the base condition here? I cannot branch. When should I not branch? If mu is equal to 0, can you branch? If, look, I'm saying that I'm going to measure. So what was in the traditional? Is there a vertex cover up size at most 0? Then what did you do this for this? He said you check whether the graph has an edge or not an edge. Right? If your graph did not have an edge and k equal to 0, he said yes, it's correct. Yes, returned it. And if graph had an edge and k was 0, he said no, it's a no instance. So what is that base condition for this algorithm? You cannot branch because you have nothing more. Imagine your money, I only give you 10 rupees to perform your job, and the moment your 10 rupees is done, then you can only do some free thing, which is, what is free in this algorithm? That's some polytime algorithm. That's the only thing which is free. So when I should be able to do some such analysis as we did just now. Oh, graph is non-empty, k is 0, say no instance. Graph is empty and k is 0, say it's a yes instance. Something of this nature, but now it will be much more complicated algorithm. Okay. Okay. So it's very important that base cases are properly taken. So what is our base case? So base case is mu is equal to 0 or less than equal to 0. How do I handle this? So what is this mu is less than 0? It's like k minus LP of G, or Or in other words, how do we know that given a graph G, there exists a vertex cover of this graph whose value, like integral vertex cover or minimum vertex cover, whose value is equal to LP of G. For example, this algorithm needs to solve what is a graph class where LP value is equal to vertex cover is bipartite graph. It needs to solve bipartite graph in polytime as in the Bates case. You get my point? Because forget about this FPT algorithm, right? If K is equal to LP of G, if this K minus LP G, you are deciding whether this graph has a vertex cover whose size is equal to the value of its LP. How will you test this in polytime? Why? Prove that this statement implies the graph is bipartite. I just said that there is a family of graphs called bipartite graphs where LP value is equal to the value of K. So this, but that's just one family of graphs. But there are many other family of graphs where this quantity could be equal. How am I going to solve this? Okay. Do you see this point? No. What is happening? Suppose there is an integral solution. There exists an integral solution whose value is equal to LP values. Then can all half be unique solution? Look at this graph, right? So look at this. Suppose this is, if I assign this as 1 and everybody else as this as 1 and this is 0, this value is equal to LP value, right? So there exists a solution where some like non-half unique solution exist, right? So if I had an algorithm to check whether all half is a unique solution or not, if I knew this algorithm, right? So if this is a polytime solvable, this will never happen. You will always be able to modify it to some have 0, 1 and half, right? Delete. And what you know, there exists an optimum solution containing these guys, right? So this property will be inherited. So if I can prove this nicely, then that also provides me an algorithm to check whether, whether this value is equal or not, right? Is that fine, right? Because if I had an integral solution which is equal to the value of LP, then assign those guys 1 and these guys 0. What is it? That value is exactly equal to LP value by our assumption, and this is a other solution where there are no halves, and you said that all half is your unique solution. So if in a graph where LP value is equal to the integral value, then you will never get all half as unique solution. So you will keep on applying reduction and be able to solve the problem in polytime. Okay. So to be able to show that all half is a unique solution is a very powerful mechanism. Okay. But that is one thing that we need to show, that independent of something, base case needs to solve in polytime. So that is one point that we must remember. What is the second point? We are applying reduction rules. If all half is not unique solution, what were you doing? Deleting something this, right? My measure should not increase. I applied some reduction rule and my measure increased. I'm like, it shouldn't increase. If it decreases, it's perfectly fine, right? When we were doing a classical vertex cover algorithm, we said, right, oh, apply degree 2 reduction rule. If some vertex goes into the solution, that's fine. K can only drop. But now our measure is not that easy. It's like K minus some LP value. So when I'm applying some reduction rule, include some vertices, exclude some vertices, what happens to my measure? It shouldn't increase. Look, I gave you 10 rupees, right? If I gave you 10 rupees and suddenly someone comes and just cheats you and gives you 50 rupees extra, then now you can do more things, no? So that shouldn't happen, because then we will never be able to analyze our running time appropriately.
Could you repeat that all half? Why is that
this is unique solution is equal to this. Okay. Suppose someone told me that this is all half. I'm telling you all half is unique solution. Then in those graph classes, LP cannot be equal to integral solution. Why? Because suppose this is my graph G, and you ran this algorithm which tell you all half is unique solution. It returned you this. Okay. Then I'm claiming to you that you cannot have an integral solution equal to LP value. Suppose you had. Suppose. So you look at this set of vertices, which is what is the meaning of the existing integral solution? Means some set of vertices are assigned 1 and some set of vertices are assigned 0. So you assign this 1, you assign this 0, and what is its value equal to? LP value. But you said all half is a unique solution, and you are producing me a solution where there are non-half entries.
So it checks for one direction, other direction.
No, we don't need other direction. I'm not saying it's if and only if, right? I'm saying that if your algorithm did I'm saying that if integral equal to LP, this you will never get, and hence you will keep on reducing, and it will be done. Right? That's all. It's one way. I'm not saying it's two way. Right? But which implies that what will happen? I find this, I can apply these things, no? And I can keep applying this because LP value is equal to this. So you deleted this guy, whichever one guys you found, you deleted it. Remaining is an LP value for the remaining guys, right? So you can keep on applying this reduction and you will never succeed with this. Right? So if we had an algorithm to check this, I can also come up with an algorithm which, if a graph G has an LP solution which is equal to an integral solution, I will be able to find it using this algorithm. Okay. Now how will we apply this algorithm? I will tell you in a minute. Okay. So base case is very important in any of the recursive algorithm. Be it in parameterized algorithm, be it in exact algorithm, be it in polytime algorithm, you should be able to handle that in whatever the time required for the base case is. So for us, our allowed time in the base case is polytime. So we should be able to solve our problem in polytime. Okay. Secondly, whenever we apply such reduction rule in the algorithm, my measure shouldn't increase, because then suddenly, why shouldn't it increase? Think for a minute. I'm trying to bound the depth as a function of this. If you suddenly something increase, right, then it is not the function of the original object, right? So it is important that even when you are applying reduction rules, the measure, it can stay the same, that's fine, but it shouldn't increase. Or you should have some controlled way to understand this. So for beginners, let's assume that it should never increase. Right? When you are mature enough to play around with them, you can play. But for our course or for anything practically is we should always believe that measure should not increase. Like some people do is, okay, I keep some global object from where I can take something. But so your drop will be like local plus global, and it's like people can do many things, but let's not go there. Okay, so I will do those things later, but what I want to do is to give you an algorithm for this in 5 minutes and then stop. Okay, and in the next lecture we'll take further how does this applies in parameterized algorithms in a nicer way. So what I want to do, how do you test whether all half is a unique solution? And I assume that there are no isolated vertex. Because if you graph had an isolated vertex, any optimum vertex cover must assign 0. You get my point? If you have an isolated vertex, can any LP solution assign it non-zero? Because if it assign, you make it 0, and that is a lesser solution. So you can assume that no degree 0 vertices. So that's the first assumption that you can make, which implies that if you have 0, then you also need 1. because every vertex is adjacent to some edge. So if you're assigning some vertex to 0, you have to assign some vertex to 1. Okay? Okay, fine. So now I'm going to check. Okay? So first I look at G. I compute the value of LP of G. I compute. Okay? I compute the value of LP of G. I kept it aside. And now I said, okay, fine, I don't know if there is an other LP solution, which is, right? Okay, so what I do is that I ask whether, is there an LP solution whose value is equal to LP of G and it is assigned 1? So what I do, what should I do to do this? I want to check, does there exist a LP solution whose value is LP of G and XU is 1. How do I test this? Just delete it, no? Delete U, compute LP of G minus U. It gives you some value, right? It gives you some value. If this value is less than equal to 1 for this, you can assign it to 1. And if there exists an LP solution where he is assigned 1, right, then if you delete it, remaining guys do form an LP solution for the remaining graph, right? So if there is an LP solution whose, if this would have been true, then look at that. If this is true, then what happens? Look at that x, okay? Now x restricted to, where x is like this, x1, xn, x restricted to say v minus u is a feasible LP, right? And what is its value? This value is, this feasible LP has value less than equal to, rather, LP of G minus 1, right? So what I know about G, if I did have LP's solution whose value is equal to linear programming of G, LP of G, and XU is assigned 1, then you delete U, you compute the LP of this, right, and check its value. If its value comes less than equal to 1, then you know, okay, fine, let me assign 1, and I have found an LP solution which is not. So I can check this, okay? So what I will do, try for all U. If I succeeded, then I succeeded, else fail for all U. What is the meaning of that? There is no, for any U, there is no LP solution where he is assigned 1, right? So it also means there is no LP value where any vertex is assigned 0, because there are no isolated vertex. What does it imply? That so the all half is the unique LP solution. So here's an algorithmic procedure. Whatever we did in the algorithm, we can actually mimic to check whether all half is the unique solution. Okay? Is that fine? Right. So it's a very, so look, something which we have always assumed is that we can compute the LP value, LP of a graph in poly time, okay? But if you assume that as a fact, then you can play around with, okay, compute this value, if these values are like this, I can conclude this, right? So these are algorithmic deductions, right? So, and what we learned, if all half is a unique solution, then in this simple branching algorithm, my measure, which is k minus LP, drops by half in both cases. In the base case, what happens? And in the base case, I can apply the fact of this algorithm to deduce whether I can solve the problem in poly time, right? So all half being an integral solution is it's a very amazing kind of, let's say, instances. Like they're very hard instances in some sense for vertex code. Those are the real hard instances in some sense, okay? So what I have not told you, that when I apply these reduction rules, why my measure does not increase, I need to tell you. You can check. You should try to check yourself, but I will anyway do it next time, because I'm going to apply reduction rules which are much more complicated than this when I try to improve this algorithm. Okay, but I have told you every facts about it. Okay, so from now onwards, I'm going to assume that all half is the unique solution, and that is the only solution we have for this graph, because we can compute this in poly time. And if we find non-half unique solution, then we have a way to make progress. Okay, so that's it.